In this video, we are going to do some more examples involving integration by parts. So let's get right into a problem which says, let's evaluate the integral of natural log of t. So we want to find this antiderivative. All right. So if we think about doing this with integration by parts, we got to find what u is and what dv is. One of the things that indicates to me that we might want to try integration by parts is that up until this point, we haven't learned how to do the antiderivative natural log. Like even with u substitution or the methods that we've learned so far, we didn't know how to do this antiderivative. So maybe with this new technique, we might be able to tackle it. Okay, so what should the pieces be? Well, looking at the function, I see this natural log, and then I see the dt. So maybe let's let the dt be the dv portion, and we'll let natural log be the u. So we can let u be ln of t, and dv is going to be dt. And then we got to say what du is and what v is. Remember that when I do these, I like to line up the d whatevers at the bottom and the original functions up top. Okay, and then so du, derivative natural log, is 1 over t. And then I write the dt with it. For v, I need the antiderivative of this. Remember that there's technically a 1 in front of the dt. This is 1 dt. So the antiderivative of 1 is t. Okay, so we got the pieces. I'll put a thought bubble around this. So now let us do our integration by parts. Remember what that says is this integral equals uv minus integral of v du. So now if we plug stuff in, u times v gives me ln of t times t minus the integral of v, so v is t, times du is 1 over t dt. And then I can simplify this integral because the t's cancel and I'm left with just 1. And that integral is much easier to do than what I started off with. So that's an indicator that, okay, yeah, this is helping. All right, so let's finish this integral off. So we got ln of t times t minus the antiderivative 1 is t. And then because this was an indefinite integral, we got to put a plus c at the end. And we got it. That is the antiderivative of natural log of t. We need integration by parts to do it. So is there any other way we could have chosen the parts here? Well, maybe there's one other thing that we could have thought of. Like what if the ln was part of the dv? So what if dv had ln and the dv always has to have the dt? Like the only way the dt is going to get produced is if it's part of the dv. It can't be part of u because u isn't a derivative yet. So if dv was this, basically if dv was everything, well, what's left to be u? Well, if this was dv, u would have to be 1. This whole thing is technically getting multiplied by 1. Okay, so u would be 1 in that case. But this wouldn't have been helpful because whatever we pick for dv, we have to be able to do its antiderivative to get v. And we don't know the antiderivative ln. In fact, that's the problem that we are faced with. So if we pick the parts in this way, we would just get stuck because we don't know the antiderivative of this function. So that's one of the things that can help us determine our parts. Like we need whatever we pick for dv to be something we know how to do the antiderivative of. So if you pick something that we don't know the antiderivative of, or maybe it's hard to do the antiderivative of, that's probably not a good choice for dv. All right, let's take a look at one more practice problem in this video. So I got the integral of x squared times e to the 4x. So what can we let the parts be here? So the u and the dv. Well, one tip I'm going to give is whatever we pick for u, we typically want to pick something where its derivative is simpler than it. So if u were to be x squared, so a second degree polynomial, its derivative would be 2x, so the degree goes down. If instead we were to put x squared here for the dv and do the antiderivative would give me a third degree polynomial, and that's now making the power bigger, which I don't really like. We like generally reducing the powers when possible. So typically we'd want to pick something for u where its derivative is simpler than it. Okay, so I'll pick it to be x squared, and then dv will be the other stuff, e to the 4x, and then the dx is with it. So then what's du and what's v? The derivative x squared, that's going to be 2x, and then I got to write the dx with it. For v, antiderivative e to the 4x, I know there's going to be an e to the 4x, and there's something in front of it, because if I were to do the derivative, if I did the derivative of e to the 4x, we would do chain rule, because the derivative e to the stuff is e to the stuff times the derivative of the stuff, and the derivative 4x is 4. So if I had just picked e to the 4x here, its derivative would have had a 4 in front. But there's no 4 in the dv. So to kind of cancel out this 4 that's popping out, I need a 1 over 4 in front here. All right. So if we do this integration by parts, if we do this, we end up getting, so u times v first. So that's going to be x squared times 1/4 e to the 4x minus the integral of v du. So v is 1/4 e to the 4x du, so times 2x dx. So with my integral, I can simplify it a little bit. I can cancel the 2 from the top and the bottom. That leaves me with a 2 down there and a 1 up here. Okay, so overall, we have x squared times e to the 4x over 4 minus, and there's a 1/2 here, which is a constant. I can pull that out. So 1/2 integral of e to the 4x times x dx. So let's compare this new integral to the one that I started with. Well, it looks similar, except this polynomial term, it has a smaller power than it used to. So in that sense, it's making it a little bit better. But I don't know how to do the antiderivative of this just yet, but let's try integration by parts again. Let's try integration by parts again. Like, I still have a product of terms, and integration by parts once reduced the power. Maybe if I reduce the power again, it'll get rid of the variable entirely. So let's try it again. So what to let u be equal to in the dv? Well, I'll use the same strategy from last time. If I let u be that polynomial term x, its derivative is simpler than it. So du would be 1, and then of course I got to write the dx with it. dv is the other stuff in the integral. So that's e to the 4x and dx. We've already done the antiderivative of that up here. So the v would be 1/4 e to the 4x. So let's put this in a thought bubble. Let's put this in a thought bubble. So if we use our integration by parts one more time on this new integral, everything else that's in front, let's leave that as it is. So x squared e to the 4x over 4. And then the minus 1/2, leave that as it is. And then I'm going to put a big old bracket, and now do integration by parts again for this integral. So I'll get u times v, which will be x times 1/4 e to the 4x. That's u times v, minus the integral of v du. So that's 1/4 e to the 4x times 1 dx. Okay. So if I look at this integral now, where I used to have these polynomial terms, now after doing it once, the x squared became an x. After I did it again, now there's just a constant there. And now this integral is something that we know how to do. Okay, because this 1/4, this constant that's there, I can just pull that out to the front. Pull that minus 1/4 out. And then I have to do the antiderivative e to the 4x. Well, we've already done that twice here. The antiderivative e to the 4x is 1/4 e to the 4x. Okay, so overall, what we have is x squared e to the 4x over 4. And now this minus 1/2, let's distribute that to each of the terms that we have here. So that'll give me minus 1/8 x e to the 4x. And then with that last term, I'll get negative times a negative is positive. So positive, and then I'll get 1 over 32 e to the 4x. And now I got to remember my plus c. This is an indefinite integral, so now I'm going to go ahead and put that plus c. And we got it. And there we have it. So one of the takeaways from this is sometimes we have to do integration by parts more than once, as we saw here. The other tip, remember, is typically when we do integration by parts, we want to pick something for u where its derivative is simpler than it.